Hello and welcome to this very basic introduction to induction machine. In this video, I hope to cover most of the basics of the theory, the mathematical formulas uh, and models that are used for induction machine, and hopefully maybe in a later video I can explain what it does and more of the theory, how it's derived, and why induction machines are better than other forms of motors. But over here, just before we start, couple things to note. Number one, in most cases we're gonna encounter three-phase machine, and you can see here by the three different colors, red, green, and blue. And these are basically the different phases coming from the electric grid line. And number two, you're gonna have to also notice the number of poles there are. And we can see over here, there's a pole occurring between these two and these two. These are the opposites. And as you can see overall, there's this spiral, and we're gonna call this a four-pole machine. And that's why you can see here these two poles here, and there's two poles here, always in pairs. So it's also either gonna be like two pole, four pole, six pole, eight pole. In this case, it's a four pole, and we notice that because there are these two opposing poles that are created by having these uh, four wire lines for each phase. Okay, so here's the equivalent circuit. To just quickly go over through it, we have the source power, and this is a per phase model. So in other words, for each of those colored wires, they're going to come within this one. So this is the source, the power that you can supply it with. It's going to have to be AC with the given frequency. Uh, then so it's going to go into the wire, and because the wire has some resistance, we're going to count it for this RS, and that'll be the resistance we're going to call it. And then what's going to happen is that resistance, so current moving through a coil should have produced electromagnetic waves. And how we're going to present that in the circuit is to show induction coil, and that will in essence create the voltage equivalent to having a gap separation between this side and the actual so the stator side and the actual motor side, the rotor side, which is spinning. So we're going to call this XM, so the magnetization current. And so you'll notice when you turn it on, this inductor will charge up, but then at a constant current, when the current wouldn't be changing, the average current is not changing, it's gonna stay. It's not gonna take any power in. So that's equivalent of charging your core, like magnetizing your core. And once it magnetized, it wouldn't do anything within it because you already established your magnetic field. And then we have the other side here, which is now the rotor magnetic field, because now the rotor itself is a wire. Or a cage. In either case, it's going to be trying to produce a back EMF to provide the spinning force, and it also has a resistance just like the source as a wire. So we're going to call that resistance over here. But there's also that magnetizing resistance, because if relative to if the rotor is spinning relative to the stator, then what's going to happen is that there will be some magnetic force being applied, and in other words, that's going to produce a back EMF, which can be counted as resistance. So if you decide to use this equivalent circuit model, then you will say, okay, this side is the resistance that is caused by the back EMF magnetic field, which we can equate it to being a resistance R. This will be the resistance that the circuit itself has, and previously, as I said, the rest would work out. So how do we define the power loss from the source? Well, it's just this resistance over here that's going to lose the power. So we're going to say that's the power loss coming from the source. The power loss in the rotor, again, it will just be this resistance over here coming out. Notice that these two inductors wouldn't take any power away. They will just absorb the power. The air gap power, so we're going to say what's the power that's really transferred from the air gap. So we know the source can produce some amount of power, but how much is really going to go through the air gap, and we're going to use this line to separate it. So everything beyond here is what's really going in the air gap. So this is really what's happening in the rotor side when we simplify the model. And the mechanical power would be the slip, the back EMF that's really being produced. That's all what we really care about. Okay, so a couple of formulas to go into it. These really are the two most important ones that we're going to derive. So the synchronous speed, which is required for the slip, is the speed that it's supposed to be running. In other words, what the what the rotating magnetic field that's created by using the AC wave would produce. And to know that, to determine that, we're gonna have to know the number of poles, as we said in the beginning of the video, the number of poles, and then the frequency, that's the frequency of the current or voltage that's coming into the each phase. So we can use that to find the RPM of it, or we can just use the angular velocity, radians per second. These two formulas hold, and then within these two you can then form the slip, and slip is determined, it's basically relative to the rotor that's spinning, how much is the stator moving away from it, how much is the magnetic field that the stator is producing moving away from it. And this is what we're going to be using. And then with these two formulas, then you can derive a bunch of other formulas, but honestly, once you get your S, you find a omega slip can be used then to derive other calculations. You can go a lot more into this to determine what happens if, like in the previous slide, the resistance of the core changes, the resistance of the stator changes, and in each case there's a specific phenomenon that's going to be seen. But this is just a brief video. So concluding, then we'd have the two forms of connection. So each phase that we've seen, like in the beginning of the slide, each phase can be connected either through delta, which means each of the phases is connected to the other one, or it can be a Y, where all of them will have a center point and meet up. And in each case, these two respective formulas hold. So the source voltage, the line voltage, and the source current will just be √3 of that, a little more than what we're actually calculating for the initial one. And then in this case, would be, again, the voltage would be a little less, while the current would be the same as the line we're working with. And again, we can go a lot more into it, but there's not much more general I can become. So hope it helps.